Hello, here's lecture 28. The last lecture I talked about the control of appetite, the hormonal control of appetite and satiety, and sugar addiction and its effects on the brain. Now, in this lecture, I'm going to talk specifically about fructose and tell you why fructose is an important sugar for us to understand. And we're going to compare it to ethanol and the effects that it might have on the liver. All right, so fructose. First of all, why should we even begin looking at here? Well, obesity tracks fructose consumption over time. And fructose consumption is one driver of corn production. So this little cartoon I made here, corn production is being driven by big soda, partially. There's a lot of things driving corn production, but big soda is one driver. Fructose consumption is one driver of corn production. And all that fructose is basically just getting spooned into Americans, leading to the obesity epidemic that we have. So these two charts on the left are showing that I'm not claiming a causative effect yet, but I am saying that there is a correlation between corn production, corn yield in the U.S., bushels per acre per year, and the advent of obesity prevalence. So in the top one, you can see in the top one you can see total fructose production and obesity prevalence, particularly free fructose and high fructose corn syrup. The advent of those two foods back in the 70s really correlate well with this meteoric rise in obesity in our country. And all of that is described very well by the lower chart that shows corn yield in the U.S. in bushels per acre per year. All right. Yeah. And so one of the things I wanted to point out was that green triangle in the bottom there. You see that around the in the 20s. That is the advent, that HB stands for Haber-Bosch. That's when the Haber-Bosch process came on. And you can see that when we started to get that the Haber-Bosch process is what enabled us to explode the corn yield in the United States. And it's kind of interesting that Haber-Bosch has led to obesity in the United States. So, okay, there's this correlation that you just showed me between fructose production, corn fructose production, and obesity. What happens when we consume lots of fructose? What does that mean? What does it do to us? Well, let's find out exactly how our body deals with fructose. The first thing I want you to remember is that all the carbohydrates and proteins entering the blood from the digestive tract have to pass through the liver first. Remember that. So we've gone through this chart before. All the blood that goes to the digestive organs is going to return to the heart via the hepatic portal vein that goes through the liver. All of the blood that goes through the stomach, that goes through the gut, has to pass through the liver first. So because of that, the liver gets dibs on any nutrients that are being absorbed through the digestive organs. Because of that, the liver bears the burden. So let's imagine that what the path of 25 grams of sucrose might take through the body. And I'm picking 25 grams because that is the amount of added sugar that the American Heart Association says should be the maximum amount of added sugars that a woman should eat in the day. All right, so you shouldn't eat more than 25 grams of added sugar. Just to just to give you a sense of what that is an 8-ounce can, one of those small little cans of Coca-Cola, is all of that sugar. It would be in one of those cans. So 25 grams of added sugar. In fact, one of those cans of Coca-Cola would be even worse than that, because that's all high fructose corn syrup, which you'll see 25 grams of that is really bad. So, all right, let's see what happens with 25 grams of sucrose. You remember that sucrose is a disaccharide, that half of which is glucose, half of it is fructose, right? And they're holding hands, they're bonded together. And we absorb the sucrose. The sucrase enzyme that our GI tract makes breaks it up into fructose and glucose, which is about 12.5 grams of each. The 12 grams of glucose gets distributed throughout the entire body, right? So all of the cells in your body have a glucose transporter that are able to take up that glucose. Only about 20% of it gets stuck in the liver as the blood returns to the liver from the gut. About 80% of that glucose goes to the rest of the body, the brain, the muscles, etc., etc. Unfortunately, all of the fructose is concentrated in the liver, because only the liver has the transporter for fructose. Because of that, the liver, when you're eating foods that have fructose in it, such as sucrose or high fructose corn syrup, you can have 30 times the glycemic tissue load, right? So it's as if instead of having 25 grams of sucrose, you had 750 grams of sugar that gets concentrated straight in the liver. Because of that, fructose is approximately 20 times more likely to cause fatty liver. And this fatty liver is the prime cause of insulin resistance compared to consumption of glucose alone. We're going to go through this in a little more detail here. But let's compare different ways that the body uses various sources of energy. So here's some bread and white bread, about 120 calories of glucose, just the starch, the amylose, the starch that's in white bread. It's just glucose. It's not fructose. Those 120 calories, 96 calories are going to go to the whole rest of the body, and about 24 calories, 20%, is going to go to the liver. That's fine. If you exercised, then the liver has its glycogen depleted, and that glucose will just get stored as new glycogen in the liver. Nothing wrong with that. That's totally healthy, normal response. All right, you're going to take a shot of ethanol, a little glass of whiskey or something. That's 120 calories of ethanol. Ethanol is primarily metabolized by the liver. Because it's coming through the gut, it goes in the liver. The liver's like, oh no, this is not going to the rest of the body. Some of it gets through the liver, but 80% of it goes to the liver. That liver takes up 96 calories of ethanol as it gets converted to acetyl-CoA, and the body gets about 24 of those 120 calories, about 20%. So it's just the opposite of the effect of glucose. All right, so the liver outcome, that carbon in the ethanol gets stored as goes through acetyl-CoA and gets stored as fat. This leads to chronically consuming ethanol can lead to fatty liver disease, all kinds of hepatic dysfunction and dyslipidemia. So hepatic breakdown, that means liver breakdown. Dyslipidemia means bad blood fat profiles. Oxidative stress throughout the body or aging, all kinds of inflammation, and of course central systemic problems like addiction. All right, so that's ethanol. Let's compare these two scenarios to sucrose, just table sugar. 120 calories of table sugar. This is not just pure fructose, it's sucrose. So a glass of orange juice, a little juice jar of orange juice, has 120 calories. 60% of those calories are going to go to the liver. 10% as glucose of the overall calories in sucrose, and 50% of the calories, so all of the fructose calories, or 50% of the total calories in fructose, is going to the liver. So that means that overall 40% of the calories in sucrose are going to the whole body, or 48 calories. No, I'm sorry. Is going to the body. And then the liver is getting 12 calories in terms of glucose and 60 calories in terms of fructose. All right. Liver outcome is pretty similar. That carbon is stored as fat. This leads to fatty liver disease, hepatic dysfunction, dyslipidemia, addiction, etc. The effect of chronic sucrose, or particularly fructose exposure on the liver, is similar to chronic exposure of alcohol on the liver. Fructose is a chronic hepatotoxic molecule consumed in the level that humans are consuming it in. Let's see this in a little bit more detail yet again. So let's see what the liver is doing. In the upper left-hand corner, that's the gut, and we eat a bunch of starch. It gets broken down with amylase. We absorb the glucose. 20% of that glucose is going to go to the liver. The rest of it's going to go to other tissues. That glucose stimulates insulin production. The insulin opens up the GLUT2 and GLUT8 transporters, which allow the glucose to pass into the liver cell. Just to remind you, orange arrows are catabolic or breakdown pathways, and blue arrows are anabolic or build-up pathways. All right. So the glucose enters the cell and is going to go through a whole chain of transformations called glycolysis, or the breakdown of glucose. It goes from glucose 6-phosphate through several steps to fructose 1,6-bisphosphate, down to pyruvate, and eventually to acetyl-CoA. You'll remember that acetyl-CoA is the molecule, the 2-carbon molecule that gets taken up by the mitochondria and enters the citric acid cycle, which is how we produce ATP out of ADP. This requires oxygen and produces carbon dioxide, etc. All right. The citric acid cycle produces two things. It produces ATP and citrate, the ionized, the conjugate base of citric acid from the citric acid cycle. These two molecules, both of them, slow down glycolysis. There's like a feedback mechanism that says, okay, we got enough ATP here, we're making lots of citrate, slow it all down. They inhibit a key glycolytic enzyme called phosphofructokinase, which is an enzyme that's responsible for sticking these phosphate groups on fructose, making fructose 1,6-bisphosphate. And citrate also activates a key gluconeogenic enzyme called fructose 1,6-bisphosphatase. This is an enzyme that starts the wheel going in the opposite direction. So we've taken all this glucose, we've filled up our ATP supplies, and now this excess citrate is telling us, okay, well, let's do something else with all this glucose. So we start the process in the opposite direction called gluconeogenesis, the making of new glucose. That glucose in the cell gets converted into glycogen in response to insulin. Insulin signaling, another thing that insulin does is it causes glucose 6-phosphate to get stored in the body as, in the liver, as glycogen. So now let's see what happens when the diet has a lot of fructose. Fructose is able to enter the liver through the GLUT5 transporter, which is also turned on by insulin. It's the only cell in the body. The liver cells are the only cells in the body that have the GLUT5 transporter. So all the fructose that's coming from the gut is going to get sucked up into the liver and goes through a process much like glycolysis called fructolysis. It's going to break down. Lysis means breaking or cutting. It's the breakdown of fructose through a multi-step pathway that we're not going to go through in detail, of course, but it ties into glycolysis ties into glycolysis through pyruvate and eventually into acetyl-CoA. And so this also ends up saturating our glycogen reserves and gives us an accumulation of acetyl-CoA. The liver can only store so much glycogen. There's only so much glycogen that can be stored because glycogen, is built around the glycogenin molecule, the protein with all these carbohydrate branches coming off of it. That gets saturated, and then the only place for all of this carbon to go from the fructose is acetyl-CoA. But there is another pathway to relieve this overabundance of acetyl-CoA because we have all the ATP we need, we have all the glycogen. Excess acetyl-CoA gets shunted into a pathway called lipogenesis, the making of new fats. So acetyl-CoA teams up with glycerol 3-phosphate, which is a byproduct of glyceraldehyde, and insulin drives this process of taking a fatty acyl-CoA, which is a growing fat chain, and sticking it on a glycerol to make a triglyceride. Right? So the liver has all this extra carbon. It just starts storing it as triglycerides because that we've learned in the calorie chapter that triglycerides are actually a much more energy-dense way of storing carbon. It's about 9 grams of 9 calories in a fat per gram, whereas it's only 4 calories in a gram of glucose. So it's a much more efficient way of storing this carbon in the liver. But it leads to the accumulation of these intrahepatic fats that live in your liver cells. So we're going to see what effect that has. And this series of slides looks at the effect of fructose on the hepatic lipid flux, the flux or flow of fats through the liver. We've talked about the liver and fats when we were talking about lipid absorption, but I'm going to show you how that intersects with fructose consumption. So let's look at the effects of an obesogenic diet, a diet that leads to obesity. This is a diet that has high fructose, that has high added sugar, and has high fat. This is an obesogenic diet, basically the McDonald's fast food meal. So, and the takeaway is going to be that chronic fructose exposure promotes metabolic syndrome in the liver. Basically, the fructose tricks the brain into increasing the total food consumption through the cognitive processes that I talked about in the previous slide. Obesogenic diets high in fats and carbohydrates, particularly fructose, lead to excessive weight gain. So these obesogenic diets lead to a host of insulin-related disorders and distortions, such as insulin resistance, increased portal insulin. So that's increased insulin in the portal vein leading to the liver. Decreased glucose disposal from the liver. Increase lipogenesis and lipolysis. All right, so let's see what the inputs are here. we're going to look at three different inputs: fructose and glucose, which are the byproducts of sucrose breakdown. The second one would be fatty acids and glycerol, so the fats. And then the third are the lipoprotein triglycerides that are being delivered by the lipoproteins like LDL and ULDL and all that stuff. So all of this obesogenic diet is going to lead to an increase in these three different categories in the bloodstream. If you were to look at the bloodstream of a person on an obesogenic diet, they're going to have more fructose, more glucose, more fatty acids and glycerol, and increased lipoprotein triglycerides, or dyslipidemia. So first, let's see what happens with the fructose and glucose. The fructose, glucose enters the liver through the GLUT transporters that we've seen already. And in the last panel of slides, I showed how that glucose that fructose gets made into fat because the glycogen and the ATP stores in the liver get saturated. So it goes through a process of de novo lipogenesis, meaning an increased amount of intrahepatic fats or lipids. This whole process is going to get accelerated by the presence of portal insulin. So I showed you that insulin drove de novo lipogenesis in that last panel of slides, and because we have an increase in portal insulin, we have an acceleration of de novo lipogenesis. Next, the fatty acids that are elevated in the blood of people on an obesogenic diet go through a process called fatty acid reesterification, meaning those fatty acids are going to form new esters to glycerol and form more triglycerides in the liver, further accentuating the intrahepatic load in these livers. Lastly, all these lipoprotein triglycerides that are circulating in the blood, that LDL gets sucked back up. Much of it gets sucked back up into the liver through a process of lipid clearance of the blood by the liver, and that just adds to this store of intrahepatic lipids. All right, now, so that's all the inputs to the intrahepatic lipids. Let's look at how the lipids get out. So the first of the two ways that lipids are able to be mobilized out of the liver is through the synthesis of VLDL, a very low density lipoprotein. Gets synthesized and then secreted back into the blood, right? And this is to distribute the triglycerides to the various tissues in the body that need them. So that's the first output, this VLDL triglyceride that gets exported from the liver. But as the VLDL gets released, that fat is spun off the lipoprotein, and the VLDL transitions to LDL and gets reabsorbed by the liver. So it gets this feedback cycle. I mean, it's exporting the VLDL, but the body is already pretty saturated with fats and triglycerides. So it's just getting absorbed back into the liver and creates this feedback mechanism of increased LDL. The second way of exporting liver is through basically beta oxidation. So the liver, you can burn the fats off. Difficult though, and this only happens during the post-absorptive state. When there's this process called beta oxidation. And that's when you break down the fats for energy. That results in the fats producing ketone bodies that get released into the blood during ketosis. This is hard to achieve, however, because that only happens, beta oxidation only happens when your glycogen reserves are gone. So all the glycogen stored in the liver is gone, and there's no glucose in the blood, like you haven't had any carbohydrates. A person on an obesogenic diet is never going to get to that point. So this is a very difficult way and this is the best way to actually reduce the fat load, but it's very difficult. You have to go into ketosis to get the liver to go through beta oxidation. So, chronically excessive dietary carbohydrates, particularly fructose, leads to an accumulation of these intrahepatic lipids, and this is what gives us fatty liver. These increased intrahepatic lipids continue to drive the VLDL secretion, which is leading to dyslipidemia, bad blood lipids, gives us atherosclerosis, and that produces more LDL, which is just driving that feedback loop that I talked about previously. And the increase in the lipoprotein triglycerides is also going to lead to an increase in serum fatty acids and glycerol, which are also going through the process of fatty acid reesterification, further driving an accumulation of intrahepatic lipids. So diets with a heavy glycemic load are never getting into beta oxidation. So they're rarely metabolizing fats for energy, right? Nor are they in ketosis. So this whole process of beta oxidative elimination of intrahepatic fat stores never happens. Never happens. And it's a spiral. It's a spiral that's extremely hard to escape from. So let's look at the comparison between the chronic ethanol exposure and chronic fructose exposure. Of all these different symptoms, so hematologic disorders, electrolyte abnormalities, hypertension, cardiomyopathy, these problems with your heart, dyslipidemia, bad blood lipids, pancreatitis, meaning inflammation of the pancreas, obesity, hepatic dysfunction, fetal alcohol syndrome, addiction. Several of them can be seen in chronic fructose exposure. So people who have chronic fructose exposure, they certainly are prone to hypertension or high blood pressure. They are certainly prone to myocardial infarction or a heart attack. They are certainly prone to dyslipidemia or an imbalance in their blood fats. They're certainly prone to pancreatitis or an inflammation of their pancreas with an accompanying second-degree dyslipidemia. They are certainly prone to obesity. They are certainly prone to hepatic dysfunction due to a fatty liver. They are certainly prone to habituation, if not addiction, to fructose consumption. There's even instances of fetuses, babies that haven't even been born, in utero, showing insulin resistance. So pre-diabetic babies because of a chronic fructose exposure on the part of the mother. All right, so that was a pretty sobering lecture right there. Next lecture is lecture 29. It's the last one, and I talk about fructose, the perfect storm. I talk about why this problem has happened in the United States, and maybe point the way towards some how to remediate this public health crisis that our country is in. Thanks for listening.